Okay, let's start class. So last time we talked about the logistic regressions, the inference interpretations, and I think we stopped here. So for the interaction, so far we talked about the models, logistic regression models, other GLM models. We mainly focus on the main effect model. So what is main effect model? Main effect model only consider the additive effects from each of the predictors. In other words, if we fixed all the other variables and change the level or the value for one of the predictors with other variables are fixed, this variable's effect will be the same on all different level combinations for the other variable. In other words, the predictor's effect does not depend on other predictor's value. So that's called additive effect. But in practice, most of the time, this assumption is too strong, right? So the additive model is very useful if we have a small sample size data set. But if we have relatively large sample size, additive model is usually too rigid or too simplified to model the truth. Why? The reason is that the sample size is really about how much information that you have to see the truth, right? If you have very limited amount of information, that means the sample size is very small. Even though the truth is very complicated, let's say nonlinear with very complicated interactions, you still cannot model it because you have very limited information. You have just a few observations. So the best model for those small sample size data is usually the additive model. The main effect model is good enough. Why? Because of the limited information. However, if we have large sample size, that means we have enough information to disclose the sophisticated truth, which may involve with interactions, nonlinear effect, and these things. Okay, so that's why interaction is very important, especially if we have large enough sample size. Okay, and what is interaction? So interaction is not additive anymore. So that means the effect of a predictor that depends on other predictors' value. Okay, so that is the interaction. Okay, so interaction, there are many, many forms of interaction. Okay, so here for the traditional statistics textbooks, if you go to the classic statistic textbooks, the interaction is just modeled by the product of two predictors. But that's not the only form. Okay, that is one of the forms for the interaction. And why people use that? Because that's also simple. It's a simple way to model the interaction. Especially if the predictors are categorical, that's good enough. But if it's numeric, that's a very specific way of modeling the interaction by the product. Because why not by the ratio? Why not by the log of the ratio? Right? There are many ways to have the interaction. Okay, but here we only focus on the product form for the interactions. So if we have a product form of the interactions, but actually any types of interaction that allows the effect of a predictor will be different if other variables' values are different. Okay, so that's the nature of the interactions. So now let's consider an example. So that's the horseshoe crab examples. So remember last time we talked about the color, right? So we have 4 types of color: medium light, medium, medium dark, and dark. And actually we have another type called the light, but we don't have any sample in that data sets that belongs to the light group. So we only have 4 levels for the color. Okay, so here last time I mentioned that we found that if we treat the dark group as 0 and all the other 3 groups as 1, that seems to be a very reasonable way to model the 4 types of colors, because these 3, the medium light, medium, and medium dark, their effects are very much the same. Okay, and they are all very different from dark. So that's the purpose that we use the dummy variable C equals to 0 for the dark color, and if it's other types, then we just model by C equals to 1. Okay, so we just create a dummy variable with C is either 1 or 0. If it's 1, that means it's not dark. If it's 0, means it's dark color. Okay, so then we can have an interaction term in the model. So we also include the crab's carapace width. Okay, so we have the logit y equals to 1. That means it has the female crab has at least 1 satellite near it, equals to an intercept plus that's the color if main effect for the color. That's the main effect for the width, and that's the interaction between the color and width. So you can see we model the interaction through the product. Okay, so let's see what does this model mean. And by the way, these numbers are the estimated coefficient for this model, and the code is here. Okay, so if it's dark colored crab, okay, so the C equals to 0. Is that right? So if you plug in the C equals to 0, then this term is gone. And this term also gone. So what is left is negative 5.854. That's the intercept, and that's the slope for the width. So you can see, how do we interpret the intercept? This intercept is the intercept for the what? For the baseline group. What is the baseline group in the color? It's the dark color. Why? Because for the dark color, we modeled C equals to 0. That's the baseline group. That's the base group. Is that right? So this intercept in the model is the intercept for the baseline group. That's how we interpret. Is that clear? And how do we interpret this slope? So 0.2, that is the slope for the dark crab, for the baseline group. Okay, so that's how we interpret the intercept and the slope for the x. Okay, so now let's see, how do we interpret the other variables? So now let's look at the lighter crab. So that includes 3 types: medium light, medium, and medium dark. Okay, if the crab color belongs to these 3, then the C equals to 1. Is that right? So what is the model? So the logit equals to what? Now this time the intercept is this one. Why? Because if the C is 1, so you can see the new intercept is actually this one. Because C is 1, so the intercept becomes the negative 5.8 minus 6.9. So that is negative 12.8. And how do we interpret this term? This is the difference of the intercept between the dark colored crab and the lighter crab. So this is the difference of the intercept between the baseline group and the non-baseline group. Is that clear? So that's how we interpret the negative 6.9. Okay? And the slope is what? Because here now the C is 1. Is that right? So the slope becomes what? Slope becomes the 0.2 plus 0.3. So it's 0.5. And that's the new slope for the width. Okay, so how do we interpret the 0.322? And that is the difference of the slope for the width between the baseline group and the non-baseline group, between the dark color crab group and the lighter crab group. Is that clear? So that's how we interpret all 4 coefficients. Okay, so then if you know how to interpret, then the next question is, do we really need that interaction term or not, right? And that's a very natural question. And when we need that interaction, because we want, so when we do the model fittings, we want the model to be sophisticated enough to capture the truth. And also we want the model to be simple enough to have a good interpretation, right? So when we add an interaction term, we want to make sure that this is needed. Otherwise, we prefer not to add interaction term. So we need to find a way, right, to test it. So we can use the likelihood ratio test. So how do we do the test? Just as what we have done before. For the likelihood ratio test, we just compare 2 models. One model is what? Is the main effect model. Is that right? And the one model is the interaction model. So the main effect model includes what? Includes the beta 0, that's the intercept, plus, let's say, beta 1, C, that's the main effect for the color, and plus the beta 2 for the times X, that's the main effect for the width. Is that right? And also, so that's the linear part. So that's the main effect. We don't have any interaction. And the interaction model is like the above, beta 0 plus beta 1 C, right? Plus, and the beta 2 X. So this is so far the main effect model. But we also need to add the interaction model. That's the beta 3 C times X. Okay, so we have these 2 models. Is that clear? Then what we do is we have the deviance for the first model, the main effect model. And we have the deviance for the interaction model. Is that right? So what we do is we have the deviance for the main effect model minus the deviance for the interaction model. Why is D1 minus D2? Because which one has a larger deviance? Of course, it's the main effect model because the main effect model is simpler. So that's why the deviance is larger, right? So deviance 1, D1 minus D2. And that is the test statistic for the likelihood ratio test. And that follows approximately a chi-square distribution with what is the degree of freedom. The way to find out the degree of freedom is to see what is the actual parameter, the number of parameters that we included here. So the difference between these two models is this term, is the interaction term. We need one additional parameter to model the interaction. So that's why the degree of freedom should be 1 here. Is that right? Given the null hypothesis is true. So if the null hypothesis is true, then this one. And what is the null hypothesis? Null hypothesis is the main effect model is good enough. Okay, so in other words, the null hypothesis is the beta 3 equals to what? Equals to 0. Okay, so that's the null hypothesis. And alternative is beta 3 not equal to 0. So if this test study is very large, then of course we will reject the null hypothesis. So that indicates the D1 model is much worse than the D2 model. And that indicates the interaction has a significant effect. So we should include the interaction. Okay, if the difference is very small, like here, you can see the p-value is 0.28. So that means what? That means we fail to reject the null hypothesis. So that means the main effect model and interaction model has no significant difference. So then we can just go with the main effect model. Okay, so here, why the p-value is not significant? One of the reasons is that the sample contains only 24 crabs with dark color. So the sample size is not very large. So as I said before, if we have a small sample size, it's very common that the main effect model stand out. But that doesn't mean there's no interaction in the true mechanism. So in the truth, most likely we have an interaction. But why we cannot find it? Because we don't have large enough sample size. So that's why we always say we fail to reject the null hypothesis. Okay, so this is the testing the interactions. So this is the code. So we just use the GOM. C2, that's the dummy variable. 1 for lighter crab, 0 is for the dark crab, times the width. So in R, when you have, let's say, C2 star width, what does that mean? That means it includes the C2 main effect, plus it includes the width main effect. Also, plus the interaction between the C2 and width. That is the using the double using the column, double column, so width. And this means the interaction between the C2 and width. This is the main effect of the width. This is the main effect of the color. This is the main effect for the width. So using the star, C2 star width, that is equals to this model. Is that clear? It's the same. Okay. Then we can here this just shows the predicted value for the width is the same, but the color is different. This one is the dark color, and this one is the lighter color crab. And the type is response, means that it will output the probability. Okay, if type is link, if the type is link, it will output what? It will output not the probability, but the logit. Okay, so if you change the type to link, it will output the logit instead of the probability. Okay, so you can see by doing that, you can see the effect of the colors on the probability of having a female, having at least one satellite around the female. So you can see when the color is not dark, the chance of having at least one satellite is much larger. It increased by what? It's almost double the probability. Is that right? And then we can compare the main effect model, which is FIT4. FIT4 is the main effect model, okay? You can go to the previous slides to check. The FIT4 is the main effect model, and the FIT5 is the interaction model with the likelihood ratio test. So you can see this is the deviance for the main effect model, and this is the deviance for the interaction model. The degrees of freedom is 1, and the deviance is the difference of the deviance is 1.1. So you can see the p-value is very large. So that means these two models has no significant difference. So that indicates we should use the main effect model. It's good enough. Okay, so that's the interaction. Any questions? Okay, so this is section 4.5 is to summarizing the effect in the logistic regression. So we can summarize the effect through the probability. Okay, so for the numeric x, we can set other variables at their means or the medians. Then we can report the y, the probability of having y equals to 1 at the upper and the lower quartile of xj. So if xj is numeric, we can report the probability of having the y equals to 1 at upper and lower quartile of xj. So what does that mean? So that means upper quartile is the 75 percentile, and the lower quartile is 25%. So that corresponds to the box plot. If you see a box plot, right, like that. So this is the minimum. This is the maximum, right? And the top of the box is the upper quartile. We call it Q3. And the lower top, the bottom one is the Q1. That's the lower quartile. So we report it at here, the top and the bottom. So that includes 50% of the data in the middle. And why we do that? Because that can allow us to see the effect of the xj, the impact of the xj on the probabilities. Okay, so if the difference, if the probability at the upper and the lower quartile are very small in terms of the probability, then we see the impact from the xj is very small, because there's no big difference. When the xj at upper and the lower quartile, the probability is almost the same. Then we can just ignore the effect of x3, right? But if it's very large, then we know that xj plays a very important role, okay? Has a very big impact on the probabilities, okay? So like here, we can just do the predictions, setting the color at the mean and the width at the quartiles. So it shows that's the probability for the width at the lower, that's the minimum, that's the first quartile, that's the lower quartiles, that's the median, that's the upper one, that's the highest width. Okay, so you can see the difference. We can compare the lower quartile, that's 0.5, and the upper quartile, that's about 0.8. So you can see the difference is about 0.3. So that's about showing you the effect of the x of the width to the probability. But this approach has a limitation. The limitation is what? This approach is usually it is useful for the additive model. But for the model with interactions, this is not very useful. Why? Because the difference actually changes with other variables changes. And here we set the crab is at the mean. If it's changed to a different value, the difference may be different. Okay, so when you use this approach, you have to be careful. Make sure if the model has interactions, then you should choose, if you still want to use this approach, you should choose the other variables at a certain level wisely, okay? But if it's main effect model, it doesn't matter for the other variable. It's always the same. Okay, so this is another way to summarize the effect. That's through the marginal effects and their average. So this one is mainly focused on the small change in the x that will have the impact on the y's. Okay, so here we can consider a setting of the explanatory variable at which the probability is pi hat. Okay, so we can adjusting for other explanatory variables, and a 1 unit increase in the xj corresponds to approximately beta j hat times pi hat times 1 minus pi hat change in the probability. Okay, so then what we can do is we can average the marginal effects, okay, over all the samples. So that gives an overall summary of its effect. Okay, so here in the library MFX, that library in R, we have a function. So there's a function called a logit MFX, and that is a useful function to find out the average marginal effects. Okay, so here the fit4 is the additive model. Okay, using the colors and the width, and at means is false. So what does that mean? So that means the we are not setting other variables at its mean value. We are using all the possible values. Okay, and the data is crab. So it found the marginal effect for the C2 is equals to this one. And the marginal effect for the width is this one. Okay, so how do we get that? That is, they use all the observations. Okay, so I forgot, oh, here, the sample size is 174. So what it does is, for each of these observed samples, okay, so we first, let's say we have the first observation. Okay, so for the first observation, we have the pi hat, right? So we have the estimated the probability of having at least one satellite, and we have the beta j hat. That beta j hat is for the color, okay, and we have 1 minus pi hat for the first observation, and we can get the beta J hat, right? And that J is for the color, okay? So that J is for the C2, okay? Times the summation for the pi hat for the observation I times 1 minus the pi hat for the observation I. And we do the summation from I equals to 1 through 173. Is that clear? So that is the sum of the effects. And we have to do the average. So we need to divide by what? So multiply by 1 over 173. Multiply by that. So that becomes the marginal effect described here. So what does that mean? That means this is the average derivative for the color based on all the observations in the data set. That's the average derivative. Okay, so what about the width? We do the same thing, but this time the beta j is what? Not for the C2, it's for the width. Is that clear? So change the beta to the beta j to the beta for the width and do the same thing. And that's the average derivative or the average slope for the width over all the observations in the data set. Okay, so you may ask, what is the difference between these marginal effects we talk about here and this one? So it's different, okay? And the reason is because, so this one is mainly focused on the small change in x. It's mainly focused on the derivatives. So the curvatures of that variable on the response. So it looks at the derivative effects mainly. Okay, but this one is, but the previous one is looking at the probability. It's just based on the probability. It's not based on the derivatives. So it's different. Okay, so this is looks more towards the dynamic change caused by one variable. Okay, to summarize the effects through that. And this is another way to interpret for the logistic regression. Okay, so this is focused on what? This is focused on the standardized interpretation. Why? Because here you can see if we interpret the effects through here or here, we always is limited by the units of the x variables. For example, for the width, in this data set, we use the centimeter as the unit, right? So if I change the width unit to inch, then the slope will be different. Does that make sense? So the slope will be different. If I change to the meters, of course, it will also be a different. So the beta will be different and the derivative will be different. Is that right? So that marginal effect is really depends on what unit that you used for that variable. And you may ask a natural question, how about I want to have an interpretation? Doesn't depend on the unit. Can we do that? Yes. And that's the motivation for doing the standardized interpretation. Because in this way, we always use the z-scores for each x. What is the z-score for the x? So for each x, we first do an operation called a center. So we centered each x by subtracting its mean so that the mean for each centered x variable has the are equals to 0. Okay, then we divide it by its standard deviation. In other words, so after that, we are using the z-scores instead. So for the z-scores, a nice property for the z-scores is what? It's unit-free. It doesn't have a unit. Okay, but you may ask, how do we interpret the z-scores? Let's say for the first observation, okay, we have the x equals to 1. What does that mean? After the standardization, so we have the z-score is 1. So that means for this observation, the width is 1 standard deviation above its mean. That's how we interpret. So if it's negative 0.5, what does that mean? That means for this observation, the width is half standard deviation below the mean. So that's how we interpret. So there's no unit. It's unit free because the unit canceled out in here. Is that right? So then when we do the interpretations, the beta will be always the same. So if you use the centimeter, you use the inch, directly the beta will be different. But if you standardize it, all these approach, no matter what unit that you use, it will be the same. And that's called a standardized logistic regression. Okay, so in that way, we can interpret the beta j without worrying about the units that we use. So that is another way to do the interpretation. And that interpretation is based on the effects of a standard deviation change in the xj with fixing other variables. And what is that impact on the response? Okay, so that's the standardized interpretation. That's another one. And this one is to summarize the prediction performance. Okay, because the two main purpose for the statistic model fitting is what? One is interpretation, one is prediction, right? So we talk about the interpretations. So the next one is prediction, right? So if we have a model, how do we summarize its prediction performance? That's also very important, right? So here the response is categorical. So we need to have some measure to quantify its classification performance, prediction performance. Is that right? So we can summarize it through a classification tables. Okay, but for the classification tables, remember the logistic regression is output what? Output the probability to be the 1 or 0. Is that right? But when we do the classifications, we need what? We need a threshold for the probabilities. Is that right? Does that make sense? If a common threshold is by, let's say, 0.5. If the probability for this observation being 1 is greater than 0.5, then we predict as 1. Otherwise, we predict as 0. Okay, so we can use 0.5 as the threshold. And another common option for setting the threshold is by what? Is by the sample proportion of 1. If for this data set, let's say we have 60% of the samples, they have the y equals to 1. And the 40% is having the y equals to 0. So then we can naturally just use the 0.6. So if the probability of being 1 is greater than 0.6, then we predict as 1. Otherwise, it's 0. So these are the two common approach, common choice for setting the threshold. Okay, so like here, in the crab example, so here you can see the sample proportion of getting 1 is 0.64. So we fit additive models and we predict the class using the sample proportion as the threshold. Okay, so then this is table. So the first row shows the true number of crabs that has no satellite. And the second row shows the frequency of the crabs that has at least one satellite. Okay, so the first column shows the predicted crabs that has no satellite. And the second column that shows the predicted crabs that has at least one satellite. Okay, so you can see here, based on this table, these diagonal counts are the corrected classification. Is that right? And those off diagonals, like this one and this one, these are the two that has the misclassified. Okay, like this 19 crabs in here, the truth is based on what we observed, they have no satellite, but we predicted as they have satellite. But for these 36 crabs that we observed, they have a satellite, at least one satellite, but we predicted as they will not have a satellite. Okay, so these are the false positive, and these are the false negative. Okay, so you can see, so the misclassification rate, we can calculate it by taking the sum. So what is the misclassification rate? It's 19 plus 36, right? So that's the misclassified over 173, because that's the total sample size. That's the sum of these four numbers. And that will be the misclassification rate, miss rate. Okay? And what is the sensitivity? Sensitivity, remember, is the true positive rate. So that is conditioned on all the crabs that have satellites. Okay, and the proportion that we predicted as they have a satellite. So that will be what? So the sensitivity here is what? So we only consider the second column. So the sensitivity is we have 75 positive over what? Over all the positive crabs, or over all the crabs that have a satellite. That's 36 plus 75. And that's sensitivity. Is that clear? For the specificity is the true negative rate. And that is the first row. That is conditioned on all the crabs that has no satellite. Okay, and the proportion that we have the negative results. So the specificity is what? Is 43 over all the crabs that has no satellite. That's 43 plus 19. Okay, so that's specificity. And what is the correct classification rate? That's the sensitivity times the proportion of having a satellite plus the specificity times the proportion of having no satellite. So you can see the correct classification rate is the weighted average for the sensitivity and the specificity. Okay, so in practice, we always like the sensitivity to be larger, as large as possible, and the specificity also to be as large as possible. Okay, and we can also evaluate through cross-validation. or an independent test set. And you may ask, what's the difference between these? Because this approach is giving us a more objective estimation or evaluation of the prediction performance. Why? Because for this approach, it's kind of biased. Why? Because we fit the models using this data set to optimize the model performance. And then we evaluate this model performance using the same data set. But this model is fitted by optimizing the model performance using this data set. So that's why it's a biased. Okay?
Professor?
This is not data mining course. If you take my 7142, I will explain that this is there is a bias. It's biased upward. Yeah.
Professor?
Katie.
You said that we wanted both specificity and sensitivity to be as large as possible.
That's the ideal case, but in the reality, it goes always the opposite direction.
Right.
Yeah.
Okay, thank you.
I'm talking about the ideal case, but you are right. Yeah. So the cross validation and using the independent test set, that to fit the model using one data set, that we usually call the training data, and evaluate through a different data set, independent test set. And that will be a much better approach, much objective approach. Okay, so that's the. And but here using the sensitivity, specificity, classification, they all depends on what? They all depends on the threshold. Does that make sense? Because here I'm setting the threshold to be the 0.64. In other words, if I change the threshold, let's say I change to 0.5, that is another popular choice for the threshold. Then the miss rate or the correct classification rate, sensitivity, specificity, they will all be different because the threshold changes, right? So a natural question is, can we have a way to summarize the prediction power which does not depend on the threshold? Yes, there is a way, and that is based on the ROC curve. An ROC curve is called receiver operating characteristic, and that shows the sensitivity and the 1 minus specificity of the prediction for all the possible thresholds. It's actually a curve. Okay, so the ROC curve is something look like that. The horizontal is 1 minus specificity, and the vertical is sensitivity. Okay, so when we set a threshold to be very small, very low, let's say we set the threshold to be 0.1. If the probability is greater than 1, we predict as positive. Otherwise, it's negative. So then the sensitivity will be very what? If we set a threshold very low, then the sensitivity will be very high. Does that make sense? Because most of the samples will predict it as positive. So if that observation is truly positive, and the chance of predicted as positive also very high if we have a very low threshold. So the sensitivity will be very high. So for low threshold, that happens somewhere here with very high sensitivity. However, the price that it paid is what? The specificity will be very low. Why? Because most of the sample will predict as positive. So for those true negative samples, we will also very likely to predict as positive. So the false positive very high. So the specificity will be very low. However, here the horizontal is 1 minus specificity. So that will also be very high. Does that make sense? So for these points at the right end, that corresponds to high threshold or low threshold. And similarly, for those points on the left end, that corresponds to the threshold to be very high. Let's say we set 99 to be the threshold. So most of the observations will predict as negative. So the sensitivity will be very low and the specificity will be very high. But 1 minus specificity will also be very low. So that's why, just as Katie raised, so here in realities, for the same model, the sensitivity and the specificity goes the opposite direction if we change the threshold. So that's why the curve, the ROC curve, is showing the sensitivity and the specificity for over all the thresholds. Then you may ask, how do we summarize the performance? Through a curve. So we summarize the performance through the area under the curve. Through the area under the curve. So what is the rationale using the area under the curve? Because if we have a perfect model, let's say we perfectly separated the y equals to 1 and y equals to 0, then the ROC curve will be what? Will be like here that I drew, will be a square. So in that case, the area under the curve will be 1. Perfect. That's the perfect model, which perfectly separated the, like here, y equals to 1. That's y equals to 0. That's based on the model. We perfectly separate that. So then the ROC curve will be just like that. So the higher the ROC curve, the better the model performance is. Okay, so if the area under the curve is close to 1, then we know that that model is really good, doing a very good job in terms of the prediction power. If then you may ask, what about the random guess? If the model is totally useless, then the model will be through the diagonals. So then the area under the curve, we call the AUC score, will be 0.5. So that's the random guess. And you may also ask, what if we have a model is it possible we have an ROC curve is less than 0.5? That's also possible, but for this model, you can just swap the y equals to 0 and 1. Because if you change, let's say, suppose you have a model like that, then you just, by simple exchange, if this model predict y equals to 1, then you just change to y equals to 0. And if this model predict as y equals to 0, then you change to y equals to 1. Then this model will be having the ROC curve like that. Okay, so by just this simple operation, you will have a much better model. So that's why the worst model is on the diagonals. Okay, so the common rule is 0.8. If the area under the curve is greater than 0.8, we usually say this model has a good predictive performance. Okay, and if it's between 0.8 and 0.5, then it usually have a quite poor performance. If it's close to 0.9 or even greater than 0.9, then we say usually have a very good prediction performance. Okay, so that's the rule of thumbs for evaluating the model performance. And this approach does not depend on the threshold. Okay. So just to look at the AUC scores. So it's close to 0.8. I would say it's okay, right? Okay, that's the chapter 4. Any questions for the chapter 4? And by the way, I posted the homework for the chapter 4 in the Moodles and the exercises in the Moodles. So it's not due next week. Next week is Mardi Gras, so it will be due after the Mardi Gras, Monday. Okay? Okay, so if you don't have any question, let's move to the chapter 5. I've posted the slides for the chapter 5 in the Moodle. So the outline, so the chapter 5 is still the logistic regression because that's the most popular models that people use to model the binary response. Okay, and we here chapter 5 focus on the building the logistic regression models and also some application aspects for the logistic regressions for the real data. So here, the first is the strategies in model selections. And then we will talk about model checkings and some issues for the real data set. If we have some, when we have some sparse data, that means the data can be very imbalanced, okay? So what we should do. And the next is some alternative approach for the logistic regression, like through the Bayesian approach, through the penalized logistic regressions or conditional logistic regression models. And the last one is some alternative link functions that we can use for the binary response, like the linear link or the probit link. Okay, so this is the outline. So here today we will just talk about the section 5.1. Okay, and we will talk about the rest in the after next week. So the model, as I said, I mentioned that. So when we do the model fittings, we need the model to be complicated enough to model the truth, but also we also like the model to be simple, to be easier for interpretations. Okay, so we have two types of studies. So the first one is the confirmatory analysis for a restricted set of models to answer the certain questions that motivate, including certain terms in the model. So the confirmatory analysis that is focused on just a few model options, model choice. Okay, let's say we have this model with that interaction and another model without interaction. So just compare like 2, 3, 4, just a few models. And we want to choose the model among these very limited number of models that we focus on. That's called a confirmatory analysis. And that is relatively a simple task. Okay, and that we've already talked about in chapter 4. So the most useful tools that we use for the confirmatory analysis is through the likelihood ratio test. Okay, so, but another one is the exploratory analysis. That we don't have a specific set of models to do the comparisons. So here we want to explore many models. Let's say we have 10 variables. We want to explore the model space that can include up to all these 10 variables. So we have so many choice, right? So that is the focus for the chapter 5. Okay, so here, so if we have this exploratory task, so how do we select the models among a large number of choices? So the first question is, how many explanatory variables can we include it in a model? Okay, and why we need to talk about that? because here in the logistic regressions, it's not like linear regression models or regression case that is directly related to the sample size. For the logistic regressions, not only the sample size will affect how many variables should we include in the model, but also we need to see if the response is balanced or imbalanced in this data set. And if it's imbalanced, how imbalanced it is. Okay, that will also affect the number of variables we can handle in the model. Okay, because the idea is if the response variable is very imbalanced, let's say if you have a data set just have 99% of ones, but only 1% of the samples that has the y equals to 0. Okay, even though this data set may contains like 1,000 observations, but what is the number of observations that have y equals to 0? Only 1% of this 1,000. That means we only have 10 observations in this 1,000 observation sample that has y equals to 0. Okay, so in that case, the model cannot be too complicated because we don't have enough sample for the y equals to 0 to model the beta. Okay, to model the parameters. So that's the important information. So a rule of thumb is that the data should contain at least 10 outcomes for each type of y for every x. Okay, so here, what does that mean? Here gives you a simple example. So if we have a data set with 30 ones and 970 zeros in the response, then since we only have 30 in the with ones, so we cannot have more than 3x in the model. Is that clear? So that is the rule of thumbs. That works pretty well. So that means if you have an imbalanced y data set, so you need to find out the sample size for those minorities. So if the sample size for the minority is very small, then you cannot expect the model includes too many x, because that will easily lead to overfitting. Okay, so another thing that will also affect the number of variables that that a model can handle is the multicollinearity, just like the linear regressions. So when we have those several explanatory variables that are highly correlated, and that can make the interpretation very difficult. Also, that will have make the models highly unstable. Okay, and how do we handle that? One effective way to handle those multicollinearities is to select the variables. And we will see the examples in a minute. And another way to handle that is through a technique called the penalized regressions, which we will talk about after next week. Okay? So let's see the horseshoe crab example. So in this data set, we have the color, right? We have 4 class, so we can have 3 dummy variables, okay? And we have the spine conditions, and that is also a categorical variable with 3 class. Remember that we have 3 class. One is both spines are good, and the other one is good, and the other one is both are bad. Okay, so these are the 3 spine conditions. So we can use 2 dummy variables to model the spine conditions. Okay, so you can see this model. So in this model, we have these two are the two spine. So these two are modeled the spine conditions. These three are modeled the color effects. And this is the width, the carapace width effect. And this is the weight effect. And this is the intercept. So to model the logit of having at least one satellite for the female crabs. Okay, so this is the main effect model that includes all the predictors with no interaction. Okay, so we can have a very simple test to compare this model with a model that has all these 7 betas equals to 0. Why 7? Because we have 2 here, right? We have 2 here, we have 3 here, we have 1 here, we have 1 here. So if you add together, that's 3, or that's 6. I'm sorry, that's 7. Okay, so we can compare this model with an intercept-only model that only contains the intercept. Okay, and we can do the likelihood ratio test with the degree of freedom is 7 because the difference of the number of parameters is 7, right? And this shows the p-value is very, very significant. That means at least one of the betas are non-zero. Okay, so but this test is not that useful because it compared with the no model that has no variables. Okay, and but here, if we look at the summary statistics for the models, we see there's no significance for all the variables. And that is a sign of multicollinearity. Okay, so if the model itself is highly significant compared with the no model, but if you look at each variable, you didn't see any variable has significant p-value. That is a warning sign for there's a multicollinearities. And there is actually a pair of variables that are highly correlated. That is the weight and width. Because these two variables, the weight of a crab and the width of a crab, they are both describing the size of the crab, right? So they are highly correlated. And actually the correlation is close to 0.9. Okay, so you can see this is the summary of the study. So you can see all 7 variables, they have the p-values not significant. Okay, so then this is a very useful tool in the library car. Okay, so this library has a function called ANOVA. So this ANOVA is different from ANOVA function that I used before. This and these are different. Why? Because in R, it's case sensitive. Okay, so capital A ANOVA, this is the function in the car library. And what it does is it actually doing the likelihood ratio test to test each term individually. Okay, so and this shows the correlation. Okay, so you can see the likelihood ratio test shows none of these terms are significant, but the color is marginally significant. Okay, so we found there is a multicollinearity problem. So how can we handle that? As I said, one way is to select the variables. So we can use stepwise variable selection to select the variables. Okay, so for the stepwise, we have 2 types. One type is through the backward elimination. One is forward selection. Okay, so the difference between these two is the backward is start with the full model. Full model means with all the variables in the model. That's the starting point for the backward. And then each step it moves away one variable. Okay, it removes one variables at each time until some stopping criteria is met. For the forward, it starts with no model. That means the intercept only model. And then add one variable into the model each step until some stopping criteria is met. Okay, so if we have some categorical variables with 3 or more categories, then we should consider the entire variable rather than just individual indicators. Does that make sense? So if we do the stepwise, okay, let's say we want to add in the color, then we should not just add in this term one step and then some other terms next step. No, one step should include what? Should include all 3 colors, because these 3 all base are all served for to model the color effects on the Y. Okay, so we should add all 3 one at a time. And for the spine, same thing. We should add these 2 at the same time, or remove these 2 at the same time. Okay, so and another assumption or the constraint that we used for the stepwise is we should if let's say we have we only test the highest order term for each variables. So that means if we want to remove a main effect term with keeping the interaction terms, that is not valid. Okay, so we should only remove the highest order first, then remove the lowest. Okay, so similarly, when we add a term into the model, we first add the main effect for that term. Then it's possible that we can add the interaction terms that has already the main effect term in the model. Okay, so we cannot having a model, let's say, with the main effect for the X, and then having the interactions for the C and X without the main effect for the C. That is not a good model. So we can only have the C main effect and the X main effect, then we can have the interaction. Okay, just like that. And variable selection methods may not use a meaningful models. So that means when you use the stepwise selections, you have to use it with caution. Okay, so the true statistical significance is not really the same as the p-value for each individual term. Okay, so that is very important because the true statistical significance is conditioned on all these true variables in the model. Then we have that. But the p-value for the individual terms, that depends on other variables. That is model dependent. That depends on all the other variables in the model. If we included some variables which should not be in the truth, should not be in the true model, then that p-value will be different. Does that make sense? Like here, the p-value for the X in this model will be different from the p-value of X in this model. Why? Because this p-value of X only contains the interaction term here. But this p-value of X contains not just interaction, but also the main effect for the C. So you can see it's different. And also when the N is large, every term will become significant. That's another important thing. So sometimes when we have large enough sample size, you will see all the individual terms are significant. But that doesn't mean all these terms we should kept in the model. Because if we have large enough terms, always very likely that all these terms tends to be easily to be significant just because of large sample size. And similarly, if we have a small sample size, almost all the terms are not significant. That's just because of lack of information. Okay, so it is sensible to include a variable that is important for the purpose of the study and report its estimated effects, even though it is not statistically significant. So that tells us statistics and all these approach, statistics is a tool that serves for the researchers. So you cannot use the statistics as really the gold standard. It's just a tool that you can use. It's a useful tool, but that doesn't mean statistics like stepwise variable selection gives you the true model. No, it's just a tool. It's just an algorithm that helps you to identify some candidate models that may be the truth, but may also not be the truth. So if you have a strong subjective knowledge that you know that, okay, this variable should be in the model, even though it's not significant, you should enforce that model to contain that variable. Okay, so that's the takeaway message. So this section 5.1.4 shows a very useful selection approach that's called a purposeful selection that selects the explanatory variable that takes into account the issues such as the study goals, relatively statistical significance, multicollinearity, and the potential confoundings. So in these 5 steps, I think these 5 steps are not difficult to understand. So you can just read that after class, and this is called a purposeful selection. So the difference between this approach with the stepwise is that this is like a machine approach. This is just an algorithm. You give me a data set, it can always find one, but the researcher cannot have input in it, right? But this one is an adaptive approach that can easily incorporate the subjective knowledge into these procedures, okay? So let's see an example. So this is the variable selection for the horseshoe crab example. So start with the no model. So this is the first line is the no model. So the deviance is the highest degrees of freedom is that AIC is the most popular information criteria, the archaic information criteria. So we can use focus on the univariate model with the color, spine, conditions, and the width. Okay. So here, after looking at these 3 univariate models, you can see we can compare these 3 models with the no model. Okay, you can see the deviance. So obviously the color and the width, these are the 2 most important. But for the spine conditions, it's not that important because obviously it's not significant, right? But for the C and the W, they are. So the next step, very natural, it's just to include C and W, right? So that is, this is to compare with the model 2. You can see we have a big improvement. So this is also significant by comparing with 2. Then the next one is to compare with 4. Is this is also significant. Okay, if you check the chi-square tables, you will see that. And then the next step, so this tells us this seems to be a good model. Then we can add the spine, main effect for the spine. And you can see to compare this model with the model 5, it's not significant because the test statistic is 0.9. Degrees of freedom is 2, so it's not significant. But when we consider the interactions between C and W, it's also not significant. So after these steps, so what is the best model? The best model is this one, the main effect for the C and W. Because if we add S, it makes insignificant improvement. If we include the interaction, it also makes insignificant improvement. So that gives us the final model to be the model 5. Okay, so we are running out of time, so let's stop here. Next time, I will talk about the AIC and some bias variance trade-off. Any questions before we stop? Okay, so let's stop here.